All right, strap yourselves in because today we're taking a deep dive into some seriously cool black hole mysteries. And I know you guys love this stuff. We're talking about 1ES 1927 plus 654, this black hole that's an incredible 270 million light years away. And it's been putting on a show, let me tell you. Back in 2018, astronomers were watching, and get this, it's corona, that superheated glowing halo of plasma. It just vanished.
Poof.
Yeah, gone. And then as if that wasn't already weird enough, it reappeared. But wait, there's more. This black hole has also been spitting out these X-ray flashes, and they're accelerating, and scientists are baffled.
Yeah, what's really intriguing is how fast these changes are happening. I mean, the X-ray pulses, they went from happening every 18 minutes to every 7 minutes, and it happened in just 2 years.
Wow.
That's like a blink of an eye, cosmically speeding. We've never seen anything like it before in a black hole.
Exactly. So we're going to be digging into some brand new research that was presented just this year at the American Astronomical Society meeting. What could possibly be causing these X-ray bursts to speed up? And what does it tell us about what's going on near the black hole's event horizon, that point of no return?
Well, the frequency of these pulses is the biggest clue. Because they're happening so fast, It means whatever is causing it has to be incredibly close to the event horizon. That's where the black hole's gravity is the most intense. And that's where things get crazy. The energy levels near the event horizon are extreme, which explains those powerful X-ray emissions.
So what are the main theories that scientists are considering to explain this cosmic whodunit? What could be causing these X-ray fireworks?
Well, there are two main theories. The first one is that the corona itself is oscillating, kind of like sloshing back and forth. As the corona shrinks, these oscillations could actually speed up, and that would explain the increasing frequency of the X-ray flashes.
So a pulsating corona. Okay, what's the other theory?
All right, now this one is straight out of science fiction, I'm telling you. Imagine a white dwarf star, the super dense remnant of a dead star. It's orbiting ridiculously close to the black hole's event horizon. We're talking a few million miles.
Oh, hold on. A white dwarf playing chicken with a black hole. That's got to be pretty risky, don't you think?
Oh, it's a cosmic tightrope walk for sure. This white dwarf, it's being pulled in by the black hole's immense gravity, but at the same time, it's also shedding its outer layers into the black hole. This creates a kind of pushback, like a little rocket engine, and that's what keeps it from completely falling in.
Talk about living on the edge. So how does this daredevil white dwarf explain all the X-ray stuff we're seeing?
All right, so picture this. As the white dwarf gets closer to the black hole, its orbital speed increases. That's because the gravitational pull is getting stronger. And this faster movement, well, that could be causing the increase in the frequency of the X-ray flashes. It's like a cosmic strobe light, getting faster and faster as the white dwarf spirals closer.
Whoa! That's an amazing picture. A tiny white dwarf whipping around a giant black hole at breakneck speed, flashing X-rays like crazy. But if there is a white dwarf this close to a black hole, wouldn't it be emitting something else too? Something Einstein predicted a while back.
You're thinking gravitational waves, right?
Yeah.
You got it. A white dwarf that close to a black hole. It should be creating ripples in space-time.
And how do we go about detecting these ripples?
Well, that's where the European Space Agency's LISA mission comes in. LISA stands for Laser Interferometer Space Antenna, and it's basically a giant, super-sensitive gravitational wave detector in space.
Oh, yeah, I remember reading about that. It's set to launch in the mid-2030s, right?
That's right. And it's specifically designed to pick up gravitational waves in the exact frequency range we would expect from this black hole system.
So LISA could actually prove whether this white dwarf is really there, doing this incredible cosmic stunt.
Exactly. LISA could be the final word on it, and it could give us even more amazing information about this extraordinary system.
This is just mind-boggling. We're talking about actually observing physics at the very edge of a black hole. What an amazing opportunity to learn. But I gotta ask, if this white dwarf really is dancing so close to the black hole's edge, what's going to happen to it in the long run? Will it eventually get swallowed up? Or will it keep doing this high wire act for, millions of years?
That, my friend, is the million-dollar question, isn't it? And honestly, we just don't know for sure yet. But that's the beautiful thing about science, isn't it? We keep observing, we keep learning, we keep pushing the boundaries of what we know. Who knows what other secrets this black hole is hiding? We'll have to just wait and see.
Well, I don't know about you, but I'm hooked. This black hole is like a real-life cosmic thriller, and I can't wait to see what happens next. But before we get too far ahead of ourselves, let's break down what we've learned so far for our listeners. I know they're just as fascinated by this as we are.
Absolutely. So we've got this black hole, 1ES 1927 plus 654, and it's been acting really strangely. First, its corona, that halo of superheated plasma. It vanished and then reappeared. Now we're seeing these X-ray pulses that are speeding up like crazy.
Right. And the leading theory is that a white dwarf star is orbiting super close to the black hole, and that's causing these X-ray flashes. And this system could also be the perfect target for future gravitational wave detectors, like LISA.
It's a remarkable system, that's for sure. It's
Yeah.
pushing the limits of our understanding of black holes and the extreme physics that governs them.
Okay, so now that we've got the basics down, let's take a closer look at that vanishing corona. What could have made it disappear and then reappear so suddenly? What are the scientists thinking?
Well, there are a few possibilities, and each one's pretty fascinating. The first theory is that a giant cloud of gas or dust might pass in front of the black hole, and that blocked our view of the corona for a bit.
Like a cosmic curtain being drawn.
Exactly. It would be kind of like how a cloud can block sunlight here on Earth. Makes it seem dimmer. The second theory is that the black hole itself might have had a sudden change in its accretion rate. You know, the rate at which it's pulling in stuff from its surroundings.
Okay, I'm following you. So if the black hole suddenly started eating matter more slowly, it could have, starved the corona, taken away the fuel it needs to stay bright and energetic.
Precisely. Think of it like turning down the gas on a stove burner. The flame will get smaller and weaker. And then there's the third theory, and this one has to do with the crazy strong magnetic fields that surround black holes. These fields are so strong that they can really influence how the plasma in the corona behaves.
So what are the scientists saying about how magnetic fields might be involved in this whole corona mystery?
Well, one possibility is that the black hole's magnetic field lines got tangled up or disrupted somehow. This could have stopped the plasma from being heated and energized as efficiently, and that would make the corona dim dramatically.
So, someone tripped over the power cord to the corona and caused a blackout.
Uh-huh. That's a great way to picture it.
All right, so we've got three main suspects: a passing cloud, a drop in the black hole's appetite, or a magnetic field hiccup. Which one do scientists think is the most likely culprit?
Well, it's a real cosmic puzzle, and it's too early to say for sure. Each theory has its pros and cons, and we need more data to figure out which one explains it best.
Fair enough. But I gotta say, that magnetic field theory definitely has a certain, dramatic flair to it.
Yeah, I can see why you'd find it appealing. The magnetic fields around black holes are incredibly complex, and we're just starting to understand how they work.
Well, this is shaping up to be one of the most fascinating black hole cases I ever come across. A disappearing corona, accelerating X-ray pulses, and maybe even a daredevil white dwarf on a collision course with oblivion. What more could you ask for?
It's a cosmic drama unfolding right before our eyes, and we have front row seats. But there's one more important piece of this story we need to discuss: the mind-bending concept of tidal forces.
Ah, yes, tidal forces. Those unseen forces that can stretch and squeeze things near a black hole. This is where things get really interesting, especially for our potential white dwarf friend. So can you break down for our listeners what these tidal forces are and why they're so important in this story?
Sure. Imagine you've got a rubber band and you start pulling on opposite ends. What happens?
Well, it stretches out and the tension in the middle increases.
Exactly. And that's similar to what happens to an object that gets too close to a black hole. The black hole's gravity pulls much harder on the side of the object that's closer to it and less on the side that's farther away. This difference in pull creates a stretching force, and that's what we call a tidal force.
So it's like the black hole is trying to pull the object apart, stretching it out like, cosmic taffy.
That's a great analogy.
Yeah.
And if those tidal forces are strong enough, they can literally rip an object apart. Scientists call this process spaghettification.
Okay, that definitely paints a vivid picture. Now, let's bring this back to our potential white dwarf. If it's really orbiting as close to the black hole as they think, is it in danger of being spaghettified?
That's the big question, isn't it? It all comes down to how close it gets to the black hole's event horizon, where those tidal forces get really extreme.
So is our little white dwarf destined to be stretched into a long, thin strand of cosmic spaghetti, Or could it somehow survive those incredible forces?
Well, that's where the amazing strength of white dwarfs comes in. These stellar remnants are incredibly dense. They're made up mostly of what we call degenerate matter. And this kind of matter is super resistant to being compressed, so white dwarfs have this sort of super strength that lets them withstand incredible pressures.
So it's like a cosmic tug of war. The black hole is pulling on the white dwarf, trying to rip it apart, but the white dwarf's internal strength is pushing back. This is getting intense.
Exactly. It's a battle of cosmic titans. And the outcome, well, we don't know for sure. But there's a chance, at least theoretically, that the white dwarf could hold its own for a surprisingly long time, even in this extreme environment. Some scientists think that a white dwarf could potentially orbit a black hole for millions, maybe even billions of years before finally losing the fight against those relentless tidal forces.
Wow, that's incredible. Talk about resilience. But even if it manages to avoid being spaghettified, what will life be like for our little white dwarf as it orbits the black hole? Will it just keep spinning around and around forever? Or is there something else in store for it?
That's a great question, and it leads us to some really fascinating possibilities. We've talked about light and X-rays, but there's another factor at play in this cosmic drama, and it could have a huge impact on the white dwarf's fate. We're talking about gravitational radiation.
Ah, yes. Those ripples in space-time we were talking about earlier. So how do these gravitational waves factor into the white dwarf's story?
Well, remember how we talked about the white dwarf possibly zipping around the black hole at super high speeds? That fast acceleration should be creating gravitational waves, and those waves carry energy away from the system. As the white dwarf loses energy, its orbit will slowly shrink, bringing it closer and closer to the black hole.
Oh no, so even if it doesn't get ripped apart right away, our little white dwarf is still slowly spiraling towards its doom.
It's definitely a possibility. But there's another scenario that could play out, and this one is even more dramatic. As the white dwarf gets closer and closer to the black hole, those intense tidal forces we talked about, they're going to start to distort its shape. They're going to stretch it out, kind of like a teardrop.
Okay, I can picture that. It's like the black hole's pulling harder on one end of the white dwarf, making it bulge out.
Exactly. And as the white dwarf gets even closer, this distortion will become more and more extreme. And here's where things get really interesting. Some scientists have this theory that as the white dwarf gets stretched and distorted like this, it could actually start to transfer some of its own matter onto the black hole.
Wait a minute. So the black hole is like a cosmic vampire slowly draining the life out of the white dwarf.
You got it. And as this material spirals inward toward the black hole, it heats up and releases a ton of energy. This could create some of the most spectacular things in the universe, like jets of high-energy particles that blast out from the black hole's poles.
Wow, that's incredible. So even in its final act, our white dwarf companion could put on an amazing show. This whole system is full of surprises, isn't it? But before we get too carried away, let's take a quick break. When we come back, we'll explore what this research means for our understanding of the universe. What are the big picture implications of all this?
I can't wait. This is just the beginning of our journey into the mysteries of 1ES 1927 plus 654. Welcome back. I'm ready to keep exploring this amazing black hole system with you.
Me too. We've covered a lot already, from that vanishing corona to the daredevil white dwarf and those incredible tidal forces. Before the break, you mentioned that this research could really change how we understand the universe. Can you tell us more about that? Why should our listeners, who I know are hanging on every word, care about what's happening millions of light years away?
That's a great question, and it really gets to the heart of why we explore space in the first place. You see, by studying black holes, especially ones that are as dramatic as 1ES 1927 plus 654, it helps us understand the basic laws of physics, the ones that govern everything in the universe.
So it's not just about the black holes themselves, it's about using them to answer those big questions about the nature of reality.
Exactly. Black holes are like extreme laboratories where we can test Einstein's theories, study how matter behaves under really strong gravity, and see where our current understanding of physics breaks down. It's like getting a glimpse into the engine room of the universe.
So by studying these weird things happening so far away, we're actually learning more about the universe we live in, right here on Earth.
Exactly. And the more we learn about the universe, the more we see how connected everything is. The same forces that create galaxies and stars also affect the tiny atoms that make up our bodies. It's all part of one big cosmic web. And by understanding one part, we understand the whole thing better.
Wow, I love that. It really highlights how we're all connected, even to something as distant and mysterious as a black hole. But let's go back to those X-ray pulses for a second. You said they're coming from very close to the event horizon. Just how close are we talking here? It's hard to imagine the scale of these things.
Well, based on their calculations, researchers think the X-ray source is only a few million miles from the event horizon.
Wow.
To put that in perspective, that's less than 10 times the distance between Earth and the Moon.
That is mind-bogglingly close to a black hole. It makes you wonder how anything could survive in such an extreme environment.
It really does. And that's why this white dwarf theory is so interesting. If it turns out to be true, it means that white dwarfs can exist much closer to black holes than we ever thought possible. It would totally change our understanding of what can survive in these incredibly strong gravitational fields.
That's a game changer, for sure. It would be like discovering life in a boiling volcano. But let's talk about that white dwarf for a minute. We've been discussing whether it'll get ripped apart by tidal forces or slowly spiral into the black hole. But what if it survives? What would life be like for a white dwarf orbiting a black hole? Would it put on a show for us here on Earth?
Now that's where things get really exciting. One possibility is that the white dwarf, as it orbits the black hole, could start pulling material from the black hole's accretion disk. That swirling disk of gas and dust that's constantly feeding the black hole.
So instead of being eaten by the black hole, the white dwarf could actually be stealing its food. That's pretty bold.
Exactly. And as this stolen material falls onto the white dwarf, it would heat up and release a ton of energy. This could create these incredibly bright bursts of light that we could see all the way from Earth. It'd be like a cosmic fireworks show.
Wow, that would be amazing to see. But you also mentioned earlier that the white dwarf itself might be losing material as it orbits the black hole. How does that play into all of this?
That's another fascinating aspect of the system. As the white dwarf whips around the black hole at those incredible speeds, the black hole's gravity could pull away some of its outer layers. This material would then spiral into the black hole, kind of adding fuel to the fire.
So even though the white dwarf might be stealing some snacks from the black hole, it's also helping the black hole grow at the same time. It's a delicate balance, isn't it?
It really is. It's this complex interplay between the two, each one affecting the other in ways we're only just starting to grasp.
This is all so mind-boggling. I love how this black hole system keeps challenging what we think is possible in the universe. But let's go back to those gravitational waves for a minute. We know LICE is designed to detect those ripples in space-time, but can you remind our listeners why gravitational waves are so important here?
Of course. Gravitational waves give us a totally new way to observe the universe. Unlike light, which can be blocked or absorbed, gravitational waves travel through space without anything stopping them. They carry information about the objects that created them, like cosmic fingerprints revealing secrets about the most extreme events in the universe. It's like listening to the universe instead of just looking at it.
That's a perfect analogy. So with our black hole system, what kind of information could we get from gravitational waves? What secrets could they unlock?
Well, first of all, gravitational waves could confirm that the white dwarf is really there. Right now, all we have is indirect evidence from the X-ray observations. But gravitational waves would be like hearing the white dwarf's heartbeat. They would be direct proof.
That would be incredible. What else could we learn?
We could also figure out the white dwarf's mass, how fast it's orbiting, and how its orbit is changing over time. We might even be able to learn something about how fast the black hole is spinning.
So by listening to these gravitational whispers, we could gain a much deeper understanding of how this entire system works. We could learn how these two objects are interacting and how they're shaping the space-time around them.
Exactly. It's like getting a backstage pass to the most amazing cosmic show imaginable.
I have to admit, I'm a little obsessed with this whole gravitational wave thing. It feels like we're opening a new chapter in astronomy. But let's bring it back to our listeners for a moment. You've mentioned that studying black holes can help us understand the fundamental laws of physics. Can you give some specific examples of how this research might be used in other areas of science, or even in our everyday lives?
Sure. One of the most exciting areas is quantum gravity, which tries to combine Einstein's theory of general relativity with quantum mechanics. Black holes, with their extreme gravity and crazy physics, are the perfect places to test these theories.
So, by studying black holes, we might unlock some of the biggest mysteries of the universe, like how gravity works at the quantum level.
Exactly. And who knows what new technologies might come from those discoveries. It's impossible to predict, but the possibilities are endless. Just imagine Understanding black hole physics could lead to breakthroughs in energy, communication, or even space travel.
Wow, that's incredible. It really shows how even the most abstract scientific research can have a huge impact on our future. But I have to ask, with all this talk about black holes, are there any risks to studying them? Could they be dangerous to us here on Earth?
That's a question we get a lot, and it's a good one. But don't worry, the black holes we study are so far away that they pose absolutely no threat to our planet.
That's good to hear. It's amazing that these cosmic monsters that can eat entire stars are harmless to us here on Earth.
It really puts things in perspective, doesn't it? It reminds us of how vast and amazing the universe is.
Speaking of amazing, I have to say, this whole black hole system has me completely hooked. It's like watching a cosmic ballet unfold. But let's dive a little deeper into how this system is structured. We've talked about the black hole, the possible white dwarf, and the accretion disk. Are there any other parts of this system we should know about?
You're right. There's one more piece of the puzzle that we haven't discussed yet. The black hole's jets.
Jets. Tell me more. What are these jets and how do they fit into this whole story?
Black hole jets are incredibly powerful beams of high-energy particles that shoot out from the black hole's poles. Imagine a fire hose in space, spraying out matter and energy at almost the speed of light.
Wow, that's an amazing image. What causes these jets to form?
We don't fully understand it yet, but it seems to be related to the intense magnetic fields around the black hole and the way the accretion disk swirls around it. As material spirals toward the black hole, some of it gets channeled along these magnetic field lines and then blasted out into space.
So it's like the black hole is using its magnetic field to create a giant particle accelerator.
Exactly.
So how do these jets connect to our white dwarf friend and all the other crazy things happening in this system?
Well, one possibility is that the white dwarf, as it orbits the black hole, could be interacting with these jets, maybe directly or indirectly. This interaction could be why we see the X-ray emissions changing so much. And it could even affect how the corona behaves.
Wow, that adds a whole other layer of complexity to this system.
It does. And it shows how much we still have to learn about black holes and their incredible power.
It's all so fascinating. But I have to ask, with all this talk about the white dwarf's fate, what about the fate of the black hole itself? Will it just keep eating everything around it and grow bigger and bigger forever?
That's a question that has fascinated scientists for a long time. And while we don't have all the answers, we do know that black holes aren't eternal. They actually slowly evaporate over incredibly long periods. It's a process called Hawking radiation.
Hawking radiation. I've heard that term before, but I'm not sure I fully get it. Can you explain it in a way that our listeners can understand?
Imagine the vacuum of space as a sea of what we call virtual particles. These are pairs of particles that pop in and out of existence constantly. Now, near the event horizon of a black hole, sometimes one of these particles gets sucked in while the other one escapes. And when that happens, the escaping particle carries away a tiny bit of the black hole's energy, causing it to slowly shrink over time.
So even black holes, these cosmic giants that seem invincible, aren't immune to the passage of time.
Exactly. Even they eventually fade away. Though for a black hole the size of 1ES 1927 plus 654, we're talking about timescales that are much, much longer than the current age of the universe.
Wow, that's incredible. It really puts things in perspective, doesn't it? Even the most powerful things in the universe have to follow the laws of physics.
Absolutely. It reminds us that the universe is constantly changing, constantly evolving. It's a place of creation and destruction, of beginnings and endings.
This has been an amazing journey so far. We've gone deep into the mysteries of black holes, explored these mind-bending tidal forces, and imagined the fate of a daredevil white dwarf. But there's still one more part of this puzzle that we need to examine, and that's those mysterious gravitational waves. When we come back, we'll explore what LESA might reveal about this system and why these ripples in space-time hold the key to unlocking some of the biggest secrets of the universe.
I can't wait. The universe is full of wonders waiting to be discovered.
Welcome back to our deep dive into the mysteries of Black Hole 1ES 1927 plus 654. We've explored so much: a disappearing corona, a white dwarf's daring dance, and those incredibly powerful jets. But there's one more thing we need to talk about, something that could revolutionize how we understand the universe.
Gravitational waves.
You got it, those ripples in space-time. Einstein predicted them over a century ago, and now we're actually able to detect them. I know we've mentioned them before, but I think it's time we gave them a little more attention. Can you remind everyone what exactly these waves are and why they're so important to understanding this black hole system?
Sure. Imagine the universe is like a giant, stretched-out sheet.
Okay, got it.
Now, picture a really massive object like a black hole or a neutron star moving quickly across that sheet. What do you think happens?
Well, I guess it would create ripples, kind of like if you rolled a bowling ball across a trampoline.
Exactly. And those ripples, that's what we call gravitational waves. They're disturbances in the fabric of space-time caused by the acceleration of really massive objects.
So it's not just matter and energy that can travel through space, but also these waves of like distorted space-time. That's pretty mind-blowing.
It is. And the really amazing part is that these waves carry information about the objects that created them. They're like cosmic fingerprints, giving us clues about some of the most extreme events in the universe.
Okay, so we know that this black hole system, with its possible white dwarf companion, could be producing these gravitational waves. But why are these waves so important in this particular case? What can they tell us that we can't get from observing light or X-rays?
Well, for starters, gravitational waves could give us proof that the white dwarf is really there. Right now, we're just going off of that indirect evidence from the X-ray observations. But gravitational waves, those would be the undeniable proof. They show us without a doubt that there's a white dwarf orbiting super close to that black hole.
That would be incredible. It would take all the guesswork out of it. But what else could we learn from these waves?
We could also learn about the white dwarf's mass, how fast it's orbiting, and how its orbit is changing over time. We might even be able to get some insights into the black hole's spin.
So by listening to these gravitational whispers, we could get a much deeper understanding of this whole system, huh? How those two objects are dancing around each other and how they're warping the space-time around them.
Exactly. It's like having a brand new sense, a new way to perceive the universe. And that's what makes this upcoming LISA mission so exciting.
Right, LISA. The Laser Interferometer Space Antenna. We've talked about it a little bit, but can you give everyone a quick refresher on what it is and how it works?
Of course. So LISA is a giant triangular-shaped spacecraft with 3 arms, each millions of kilometers long. And at the end of each arm, there's a free-floating test mass. Now, here's the cool part. LISA is built to detect tiny changes in the distances between these test masses caused by these gravitational waves passing by.
So it's like a huge ruler in space, measuring how space-time stretches and squeezes as these cosmic ripples go through.
Exactly. And because LISA is up in space, it's not affected by all the noise and vibrations that mess with the ground-based gravitational wave detectors. That makes it incredibly sensitive. It can detect waves from sources that are billions of light years away.
That's amazing. So LISA is like this giant ear listening to the music of the universe, a music that's been playing for billions of years. We're just finally able to hear it.
That's a beautiful way to put it. And the exciting part is that LISA is going to be most sensitive to the frequencies of gravitational waves that we expect from systems like our black hole with its possible white dwarf companion.
So you could say that LISA was built specifically to make these kinds of discoveries, to unlock the secrets of these extreme environments.
In a way, you're absolutely right. It's the result of decades of research, and it has the potential to completely change how we understand black holes, neutron stars, and the whole evolution of the universe.
I'm getting goosebumps just thinking about it. It's like we're entering a new age of astronomy. We're not just using light to study space anymore, we're using gravity, too. We can now explore the cosmos in ways that we never thought possible.
It's an incredible time to be a scientist, that's for sure. And who knows what other amazing things we'll discover as we keep listening to the universe.
Well, I, for one, am ready to hear what the universe has to say. I can't wait for LISA to launch and start sending us data. But in the meantime, I think we've given our listeners a pretty incredible look into the mysteries of 1ES 1927 plus 654.
We definitely have. We've explored its vanishing corona, the possibility of a white dwarf doing this incredible cosmic dance around it, those powerful jets, and those mind-boggling gravitational waves.
It's been a wild ride, full of wonder, mystery, and the thrill of discovery. It just goes to show that the universe is an amazing place. It's full of beauty, power, and complexity. And out there, it seems like the impossible happens every single day.
You said it. And there's still so many secrets out there just waiting for us to uncover them.
So to our listeners, keep looking up, keep asking questions, and never stop exploring the wonders of the cosmos. Who knows what incredible discoveries are waiting for us out there?
Until next time, keep diving deep.